Welcome to the Deep Dive. Today we're diving deep into something genuinely transformative, multimodal AI. Think of this as us, cracking open the source code for what people are calling the next frontier in artificial intelligence. We've got a stack of research papers, articles, notes, basically your all-access pass to get a quick but really thorough understanding. Our mission for this deep dive, it's pretty straightforward. We want to unpack what multimodal AI actually is. We'll peek behind the curtain a bit, see how it works, explore its, frankly, incredible potential and what it can already do, wrestle with some of the big challenges it's facing, and get a sense of where it's all heading next. All tailored so you, our listener, can get up to speed on this complex but really crucial topic. The way you understand the world, it isn't through just one sense, right?
Right.
You see, you hear, maybe you touch something all at the same time. Integrating all that information.
Building a complete picture.
Exactly. The real world is like it's a symphony of different data types coming at us. And that's, I think, exactly why multimodal AI matters so much. It's AI learning to perceive and interact with the world. Well, more like we do. Okay, let's unpack this.
Right. That's the core idea. So multimodal AI refers to AI systems, models that can process and crucially integrate multiple types of data simultaneously. We call these different data types modalities.
Modalities, right. That's a term for just kind of data.
Exactly. So, text, images, audio, video, those are the classic ones we talk about most. But the sources show the field is already pushing beyond that. We're seeing things like computer code, mathematical formulas.
Wow. Good.
Even 3D depth information, thermal sensor data, movement data. The real power isn't just handling these individually, though. It's the AI's ability to bring them together, to fuse them for a more complete understanding.
So it's not just like juggling different balls, it's understanding how the balls relate to each other.
Precisely. Compare that to what we usually call unimodal AI. Think about those early text-only chatbots, or maybe an image recognition system that only did images. They were effective, sure, but only within their narrow lane.
Limited scope.
Totally. Multimodal AI breaks out of that. By processing multiple modalities concurrently, it can grasp much more complex scenarios. It can deliver richer, more context-aware responses because it sees the picture and reads the caption, or hears the audio and sees the action in a video.
So it gets a much more comprehensive view. It can catch nuances that a single-sense AI would just miss.
Yes, exactly. That comprehensive understanding is probably the key advantage. It tends to lead to more accurate outputs. It makes the AI more robust, too.
How so robust?
Well, if one data stream is noisy, say the audio is bad or maybe even missing entirely, it can potentially rely on the other modalities like the visual information to fill in the gaps.
Oh, okay. Makes sense.
And maybe most importantly for us users, it enables much more natural human-computer interaction. Think about talking to a virtual assistant that doesn't just process your words.
But can also maybe see what's on your screen or understand your tone of voice from the audio.
Right. That feels less like just using a tool.
Yeah.
And more like interacting with something that, well, kind of gets it.
Exactly. Something more intelligent.
I remember when chatbots first let you upload an image. That felt multimodal, but you're saying that wasn't quite the real deal.
No, and that's a really crucial distinction the research highlights, this difference between apparent and native multimodality.
Okay.
Apparent multimodality is basically chaining separate specialized AI models together. Like you use one model for speech to text, another AI generates an image, maybe a third one processes the text separately. They're linked, yes, but the integration is shallow.
They weren't designed together.
Right. They don't inherently understand the deep connections between the sight and sound, so to speak, from the get-go. Native multimodal models like Google's Gemini or OpenAI's GPT-4o that we're seeing now are different. They are built and trained from the ground up to handle different data types together simultaneously.
Ah, okay. So it's like building a brain that naturally has eyes and ears, rather than just bolting on separate modules for sight and sound later.
That's a fantastic analogy, actually, yeah. Native models learn those really intricate cross-modal relationships, how sound relates to visuals, how text describes an image organically during their training process. They tend to be more efficient, often faster, and they can achieve a much deeper level of integrated understanding. It's a really significant evolutionary leap in AI.
And this didn't just, pop up overnight, right? There's a history here.
Oh, absolutely not. The core ideas go back quite a way. Things like audiovisual speech recognition, combining lip movements with sound that's been researched for years. Early approaches often involved a lot of manual feature engineering.
Right, humans telling the AI what to look for.
Exactly. Then deep learning came along. Convolutional neural networks, CNNs, got really good at images. Recurrent neural networks, RNNs for text and sequences. People started training models on bigger data sets like ImageNet and began exploring how to learn representations that bridge different data types.
And then came the transformer architecture. That seems to be everywhere now.
It was absolutely pivotal. The transformer's design is incredibly flexible. It's sort of modality agnostic.
Meaning it doesn't care as much what kind of data you feed it.
Pretty much. You can apply the same core principles to text or image patches or audio segments. It treats them all as sequences of information. That was a major breakthrough. That flexibility, combined with the explosion in availability of truly massive multimodal data sets.
Data containing text and images and audio all linked together.
Exactly. That combination allowed researchers to train these enormous integrated models that represent the current wave of native multimodality. It's a clear convergence trend moving towards AI that's more general purpose, less confined to just one task or one type of data.
Okay, that makes a lot of sense. A flexible architecture finally met the massive, diverse data needed to train it properly. So let's peek behind that curtain then. How does an AI actually do this integration of sight, sound, text? What are the mechanics?
It's definitely sophisticated, but yeah, we can break it down into, let's say, 3 core ideas or stages. First, the AI has to process the raw data coming in from each modality, pixels, waveforms, characters. Second, it needs to transform that processed data into, well, a kind of universal language that the AI can understand internally, a common format.
Okay, translate everything.
Sort of, yeah.
Yep.
And third, it needs ways to combine or fuse this translated information strategically.
Processing, translating, fusing. Got it. Let's start with step 1, getting the raw data ready.
Yeah.
How do you turn, messy real-world stuff into something the AI can work with?
Right, because real-world data is inherently heterogeneous, right? Totally different formats. So the AI needs specialized pre-processing for each type. For vision images or video frames, it often uses those CNNs we mentioned. They're good at extracting features hierarchically, like starting with simple edges, then shapes, then maybe recognizing objects. You also do basic stuff like resizing or normalizing images. Computer vision techniques refine this.
Okay, so breaking down the visual scene.
Exactly. For language text or transcribed speech, it uses natural language processing, NLP. That involves things like tokenization, breaking text into words or subwords, maybe stemming, or lemmatization to get root words, removing common stop words. Computational linguistics helps understand syntax and semantics. Ultimately, statistical NLP often maps language into numerical vectors or embeddings. This conversion is fundamental.
Turning words into numbers the AI can crunch.
Precisely. For audio, it starts with the raw acoustic signal. Techniques involve transcription, maybe speaker recognition using acoustic models, plus language models. Noise reduction is often key. Then feature extraction, identifying things like pitch, frequency patterns. You convert the raw waveform into representations like spectrograms or MFCCs.
Like a visual fingerprint of the sound.
Kinda, yeah. And recently, there's focus on source-centric representations trying to disentangle individual sounds within a complex audio scene, a bit like how our ears focus. This helps a lot when you fuse audio with other data.
Makes sense. What about other data, like from sensors?
Yeah, sensor data, think IoT devices, LiDAR in cars, GPS coordinates. That also needs transformation. Challenges there include interpreting discrete data points, understanding temporal behavior, dependencies between sensors. The goal is always to convert raw, often noisy, high-volume signals into smart, data-relevant, high-quality information, often using AI algorithms right at the pre-processing stage.
And video's kind of a mix.
Video combines image processing for the frames and audio processing for the soundtrack, but with a crucial focus on temporal alignment, understanding how things change over time, and how the sound matches the visuals.
Okay, so that's pre-processing, getting the raw stuff into a more structured feature format. Step 2 is the translation part, representation learning.
Exactly, representation learning. This takes those process features and transforms them into compressed, meaningful patterns the AI can really work with. It's vital because it makes the data more interpretable for the AI, helps uncover important underlying features, and allows for things like transfer learning, using knowledge from one task to help with another.
What's the goal here? Just make it smaller.
Not just smaller in size, though, that helps. The goal is to map the raw data, let's call it X, to a compressed representation, Z, that is invariant to nuisance factors.
Nuisance factors,
Well, like variations in lighting in an image, or background noise in audio, or maybe slightly different phrasing in text. You want to discard that irrelevant stuff and keep only the essential, semantically meaningful information. It's like Occam's razor for data.
keep it simple, keep the important stuff.
Right. Deep neural networks are very effective at learning these compressed representations automatically. Compression here isn't just about file size, it's about relevance, enabling efficient storage and retrieval, faster model training, and creating a more universal understanding.
And this leads to the idea of a shared space.
Yes, joint embedding spaces. This is a cornerstone concept. It's about learning these joint representations where data from distinctly different modalities, images, text, audio, are all mapped into a single, shared, high-dimensional space.
A universal map for meaning.
Exactly. The key idea is that semantically similar things end up close together in this space, regardless of their original modality. A picture of a dog, the word dog, maybe even the sound of a bark, they should all cluster near each other.
So it preserves meaning within each data type, but also across them.
Precisely. This is typically learned using deep networks, often with some shared layers where the information streams converge. You might have a CNN processing the image, an RNN processing the text, and they feed into layers that learn this common space.
Meta's image bind work, that was about this, right? 6 modalities in one space.
Yes, that's a prime example. Think of this joint space as a kind of universal translator for the AI. It bridges the heterogeneity gap, the fundamental differences between data types. It's absolutely essential for enabling the AI to do cross-modal reasoning, like searching for images using text or generating text descriptions for videos. It lets the AI build that coherent understanding from all its different inputs.
Okay, so process the data, translate it into a shared meaning map.
Okay.
Now, step 3, fusion, combining the info.
Yes, fusion techniques. This is the process of actually combining those synchronized features from the different modalities, often after they're in or near that joint space, into a single unified representation. There's usually a specific fusion module in the AI architecture that does this. Its job is to bridge that heterogeneity gap further, correlate the semantics, and ultimately boost the model's performance.
Is there one best way to fuse the data?
No, there isn't. It involves strategic trade-offs, and the best approach really depends on the specific task and the data you have. There are 3 main strategies people talk about.
Okay, what
First is early fusion, or feature-level fusion. Here, you merge the raw data or the very initial features from each modality right at the beginning of the process. Maybe just concatenate the feature vectors.
Just stick together early on.
Right. The advantage is you preserve all the information, and the model can potentially learn complex interactions between modalities immediately, like how specific visual features relate to specific words.
But the downside?
It can result in very high-dimensional vectors, which means high computational cost, lots of memory needed, and you often need careful normalization to make sure one modality doesn't dominate just because its numbers are bigger.
Okay, so early fusion. What else?
Then there's late fusion, or decision-level fusion. This is the opposite extreme. You process each modality completely independently through its own dedicated model pipeline. Only at the very end, when each pipeline has made its prediction or decision, do you combine those outputs. Maybe you average the predictions or use a simple voting scheme.
So keep them separate until the last moment.
Exactly. The advantages here are that you can optimize each pipeline specifically for its own modality. It's often more robust if one modality is missing entirely. The other streams can still produce an output. And it can be more interpretable because you can see the individual predictions before they're combined. The main disadvantage is that you might miss out on subtle interactions or correlations between the modalities that would have been useful earlier in the processing. The fusion happens too late to influence the feature learning itself. You might also end up relying too heavily on just one modality's prediction.
Makes sense. So early, late. Is there something in the middle?
Yes, and that's intermediate fusion, sometimes called mid-level or joint fusion. Here, you do some initial independent processing for each modality, but then you merge the information at intermediate layers within the network architecture. The goal is to capture more complex relationships than late fusion allows, but maybe be more manageable than super early fusion. This often involves techniques like cross-modal attention, which we should talk about.
Okay, so balance. What are the trade-offs there?
It tries to get the best of both worlds, allowing for nuanced understanding through these interaction points deeper in the network. But the architectures can become more complex to design and potentially require more computational resources than late fusion.
So the choice depends on the task, the data, and what you're optimizing for efficiency, maybe interpretability, or capturing those deep cross-modal links.
Exactly. Careful design is needed, and closely related to fusion is cross-modal alignment.
Alignment, making sure the right bits connect.
Precisely. After processing the features, maybe even putting them in a joint space, you still need to explicitly align them. Identify the connections and interactions between the modalities. This is challenging because of that inherent heterogeneity. Text has words, images have regions, audio has time segments. The correspondences can be complex.
Like matching the spoken word dog to the pixels representing the dog.
Exactly. Cross-modal learning methods are designed to establish these associations. The text context can help the image recognition part, or visual information can improve the generated text description. The goal is semantic coherence. If the text says red ball, the alignment mechanism needs to make sure the model is linking that to the features of a round red object in the image.
Without that alignment, the fusion step wouldn't really know what parts relate to each other.
Right, it would just be mixing potentially unrelated features. And this is where attention mechanisms become absolutely indispensable.
Attention again. You mentioned cross-modal attention. How does that work?
Attention mechanisms are powerful tools that let the model dynamically focus on the most relevant parts of the input data and, crucially, the interactions between those parts. They work by computing weights or attention scores that determine how much focus to put on different pieces of information.
Okay.
Cross-modal attention specifically bridges distinct data types. Let's take that visual question answering example. You show the AI an image and ask, what color is the car? The text embeddings for color and car act like a query. The attention mechanism uses this query to scan the image features. It calculates high attention scores for the visual region corresponding to the car, especially features related to its color, while maybe ignoring the background or other objects.
So it uses the question to guide where in the image to pay attention.
Exactly. It dynamically identifies and weights the relevant cross-modal connections. This is different from self-attention within a single modality where, say, words attend to other words in the same sentence.
What are the big advantages of using attention here?
Several key ones. Attention mechanisms can handle inputs of varying lengths naturally. They're great at capturing long-range dependencies connections between distant parts of the input. They enable context-aware processing. Information can flow bidirectionally. And they offer some level of interpretability. You can often visualize the attention weights to see what parts of the input the model focused on for a given output.
That dynamic focus seems central to getting that fine-grained understanding needed for multimodal tasks, filtering the noise, prioritizing the signal.
Absolutely. And all of this, the processing, the representation, the fusion, the alignment, the attention, has increasingly been implemented using transformer architectures.
Back to the transformer. Why has it become such a backbone?
Because, as we said, it's fundamentally modality agnostic at its core. It treats input as sequences of tokens, whether those tokens originally came from text or image patches or audio segments. You need ways to tokenize each modality, first turn images into sequences of patches, audio into chunks, and then embed them, project them into a vector space the transformer understands.
So you turn everything into a common format first.
Right. It often uses special tokens, like a CLS token, to represent the whole sequence. And crucially, it needs position embeddings to retain information about the order or spatial location of tokens, since the core transformer doesn't inherently know sequence order.
Okay, and the attention part within the transformer.
The key is self-attention, SA, and multi-head self-attention, MHSA. Self-attention allows every token in the sequence to attend to every other token. This gives it a kind of global perception. MHSA just stacks multiple self-attention layers, allowing the model to attend to different aspects or representation subspaces simultaneously.
And how does it handle the cross-modal interactions using just self-attention?
Primarily through variants of self-attention applied to combined sequences. You might simply concatenate the token sequences from different modalities, like text tokens followed by image patch tokens, and let the self-attention mechanism figure out the cross-modal relationships. Or you might use more sophisticated cross-attention layers, where tokens from one modality attend specifically to tokens from another.
So the transformer's core mechanism is flexible enough to learn these connections.
Exactly. Its unifying power, its modality-agnostic nature, and the ability to model everything as sequences or even graphs allowed the field to move beyond highly specialized, separate architectures for each modality combination. It enabled the creation of these large general-purpose foundation models that can learn complex interactions efficiently across many data types. This really propelled the field forward into the era of native multimodality we're in now.
Wow, okay. That's a lot under the hood, but it paints a picture of how these systems are built. So, with all that complex machinery working together, what's the real-world payoff? What's the impact?
The impact is truly profound. It represents a massive leap beyond the limitations of single-modality AI. First and foremost, you get enhanced understanding and robustness.
We touched on this, but expand a bit.
By integrating information from multiple sources, text, image, audio, these models achieve a much more comprehensive, nuanced interpretation of situations or data. It's synergistic.
The whole is greater than the sum of the parts.
Pretty much. This leads to demonstrably higher accuracy and better robustness across a wide range of tasks: image recognition, translation, speech recognition, you name it. They capture richer context. Think about human communication. A smile combined with a sarcastic tone of voice means something very different from just the smile or just the words. Multimodal AI can start to grasp those kinds of nuances.
Which unimodal AI would totally miss.
Exactly. And as we mentioned, they're more resilient to noise or missing data because they can often rely on the other available modalities. All this fosters a more human-like, common sense understanding. It allows the AI to interpret context and nuance better, making it potentially more reliable and trustworthy when deployed in the messy, unpredictable real world.
Beyond just understanding better, does it enable new kinds of thinking for AI?
Yes, absolutely. It unlocks advanced reasoning and problem-solving capabilities. These models can synthesize knowledge from multimodal evidence. They can follow multiple inferential steps, piecing together clues from text, images, audio, even code, to arrive at conclusions or solutions that would be impossible otherwise.
Like Google, showing Gemini reasoning through a physics problem presented visually.
Precisely. It can tackle complex problems that inherently require understanding across different domains or data types. This facilitates much more sophisticated decision-making, closer to how humans integrate diverse information streams.
So what are some of the really cool general capabilities we're seeing emerge from this?
This is where it gets really exciting because it fundamentally alters how we can interact with digital content and information. A key characteristic is the ability for any-to-any input-output.
Any-to-any?
Yeah, the ability to process inputs from pretty much any combination of modalities: text, image, audio, video, code, and then generate outputs in any of those content types.
Wait, really? So text prompt to video, image prompt to audio?
Yes. Text to image we're familiar with, but also image to text, captioning, text to video, text to audio, even potentially text or image to 3D models. This versatility is a direct result of those joint representations and fusion techniques we talked about.
The AI learns the underlying concepts and can map them across different media formats.
Exactly. And this enables incredible content generation, creating rich multimedia images, videos, music, synthetic voices, 3D assets. It's revolutionizing fields like entertainment, gaming, architecture, education. Think faster content pipelines, personalized media.
What about using it on existing stuff?
Big impact there, too. Information extraction and summarization. Think about automatically converting complex documents, scanned PDFs, with text, tables, and images, or even handwritten notes into structured, usable data. That uses OCR combined with visual understanding and NLP, or summarizing a long video meeting based on both the visuals shown and the audio discussion.
That'd be amazing.
Then there's cross-modal retrieval and search. Searching your photo library using a voice query, or finding relevant video clips based on describing the action, not just keywords. It improves accuracy and relevance significantly.
And understanding really complex events.
Yes, understanding complex scenarios. Analyzing, say, security footage by processing both the visual feed and the ambient audio to get a full picture of what happened. And we shouldn't forget code generation. Models like Gemini can understand code, explain it, and generate new code, potentially even translating between programming languages or generating code from diagrams or descriptions. That's a huge productivity boost for developers.
It really feels like this generative versatility, this any-to-any capability is the game changer. It's not just analyzing, it's creating and transforming information across boundaries.
It is. It represents a fundamental shift in how we create and interact with digital media. It enables a kind of creative synthesis, blurring the lines between different forms of expression.
So, stepping back even further,
What are the big societal implications? How does this change things on a broader scale?
The implications are wide-ranging, touching everything from how we interact with tech to employment, creativity, and entire industries.
Like how we talk to our devices.
Definitely. Enhanced human-computer interaction, HCI, is a big one. It makes interacting with technology potentially much more natural and intuitive, more like talking to a helpful person than issuing commands to a machine. Virtual assistants that understand your voice and see visual cues on your screen or in your environment.
And accessibility.
Huge potential for improved accessibility. Systems that can combine text-to-speech with visual descriptions or interpret sign language visually, accommodating diverse needs and making information more universally accessible.
What about industries? Which ones are being impacted?
It's hard to find one that won't be impacted, honestly. Revolutionizing industries is happening across the board. Healthcare. Think diagnostics combining medical images with patient history text and maybe even audio analysis of coughs. Transportation. Autonomous vehicles rely heavily on fusing sensor data like LiDAR, cameras, radar. Retail. Smarter shopping experiences, virtual try-ons. Content creation, obviously. Security and surveillance. Manufacturing quality control. Finance, education, telecommunications, the list goes on.
It seems pervasive. You mentioned this idea of super agency earlier. Can you unpack that a bit more? It sounds significant.
It is a really interesting and potentially powerful concept. The idea is that multimodal AI could amplify human agency, effectively giving us superpowers.
Superpowers, like what?
By acting as this incredibly capable co-pilot or research assistant that deeply understands information in all its forms, it can dramatically supercharge human creativity, productivity, and our ability to make a positive impact. It can lower the technical skill barriers for complex tasks, maybe designing something complex without needing years of CAD training, just by describing it and showing examples. It shifts how we access and utilize knowledge.
So AI isn't just replacing tasks, it's augmenting our own intelligence.
That's the core idea of superagency. Enabling new forms of collaboration between humans and AI, potentially unlocking waves of innovation and growth. Think about the productivity gains. McKinsey and others project substantial economic growth from AI adoption, and multimodal capabilities are a crucial part of that picture.
That shift towards superagency feels really important. If the AI can handle pulling together information from documents, videos, spreadsheets, it frees you up.
Exactly. It reduces the cognitive load for users, allowing focus on higher-level strategy, creativity, critical thinking. It also suggests potential shifts in education, maybe focusing more on AI literacy and how to partner effectively with these tools.
Okay, this all sounds incredibly promising, almost utopian in some ways.
Yeah.
But there have to be downsides, right? Challenges, ethical minefields.
Oh, absolutely. For all its power, multimodal AI faces significant hurdles for widespread adoption and, crucially, for responsible development.
Let's start with the technical stuff. What are the big roadblocks there?
Well, we touched on data integration complexity. Just the intricate nature of getting these fundamentally different data types, unique formats, structures, quality levels to align and integrate smoothly, especially at scale, is really hard. This can lead to real challenges with real-time processing and latency.
Trying to stitch together apples and oranges and audio waves in real time.
Kinda, yeah. And that directly ties into scalability. These large, often parallel network architectures needed to handle multiple modalities require substantial memory and processing power GPUs, TPUs.
Expensive hardware.
Right, which limits accessibility.
Right.
And deploying these huge models on edge devices like your phone or a smart camera requires aggressive optimization techniques like pruning or quantization, which can sometimes hurt accuracy. It's a trade-off.
So complexity makes scaling hard, and scaling efficiently is tough.
And then there's the real world being messy, handling noisy or incomplete data. Real-world inputs are rarely perfect studio recordings or crystal clear images. You get background noise, blurry photos, missing modalities altogether.
The AI has to cope with bad data.
Exactly. Building robust pre-processing pipelines and models that can handle this non-uniformity adds yet another layer of complexity. And these challenges are all interconnected, right? Integration complexity makes scalability harder. Noisy data complicates integration. You can't really solve one without considering the others. It requires holistic solutions.
What about the black box problem? Understanding why it made a decision. Is that worse with multimodal?
It can be, yes. Interpretability remains a major challenge. Many of these powerful multimodal models, being based on deep learning, function as black boxes. It's difficult to trace the exact reasoning path, especially when it involves complex fusion and attention across different data types.
And that matters?
Why? It leads to skepticism and lack of trust, especially in high-stakes applications. Think healthcare diagnostics or legal analysis or autonomous driving. If the AI can't explain its reasoning, how can we rely on it when the consequences are serious?
Right. You need accountability.
Exactly. Techniques like attention maps can offer some clues showing where the model looked, but they might not provide a full causal explanation and aren't always practical for real-time systems. Building trust requires interpretability. It's both a technical and an ethical imperative. Research into explainable AI, XAI, specifically multimodal XAI, MXAI, is crucial but ongoing.
Okay, so technical hurdles to the black box. What about bias? We hear a lot about bias in AI generally.
Bias and fairness are absolutely critical concerns, and they manifest in unique ways in multimodal systems. Like other AI, these models can inherit and even amplify biases present in their training data. If the data used to train them is skewed, maybe underrepresenting certain demographic groups in images or reflecting societal stereotypes in text, the model will learn those biases.
So biased data leads to biased AI.
Yes, but there's a specific concern in multimodal AI. Modality biases.
Modality bias.
Yeah, this is where the model learns to rely too heavily on one modality over others, even when multiple are available. For example, a vision language model might predominantly trust the text description associated with an image, even if the visual information contradicts it, or vice versa.
So it ignores potentially useful information from one of its senses.
Exactly. This can lead to suboptimal performance, reduced robustness, and importantly, unfair or skewed outputs. We've seen examples of gender or racial biases in image captioning systems or search results generated by these models. Discrimination can be embedded and scaled.
That's worrying. How do you even begin to fix that?
It requires a multifaceted approach. It's not just one thing. First, data auditing and pre-processing. Carefully examining the training data for imbalances, using fairness metrics, inspecting potential labeling biases, then trying to mitigate it through techniques like rebalancing data sets, maybe generating synthetic data for underrepresented groups.
Cleaning up the input.
That's part of it. Then algorithmic testing during inference. You need to actively test the deployed model's responses. See how it behaves when presented with inputs related to protected attributes like race or gender. Use adversarial testing to probe weaknesses. Check for consistency across modalities. Does it say one thing based on text and contradict itself based on the image?
Testing how it actually behaves.
Right. And real-world monitoring. Continuously monitoring its performance in the wild through user feedback, A/B testing across different user groups, logging inputs and outputs to catch problematic patterns as they emerge. It has to be iterative. And finally, architectural adjustments. Researchers are developing techniques within the model architecture itself, things with names like prompting, IVTP, cross-attention projection, specifically designed to encourage better balance and integration between modalities, reducing that over-reliance on just one.
So data, testing, monitoring, and even tweaking the model's design. It sounds complex.
It is, and sometimes these mitigation techniques can even slightly decrease overall accuracy on standard benchmarks, so there are trade-offs to manage carefully. Bias is systemic. It's not just the data, but how the model learns and potentially propagates bias. Modality bias is a failure to use all available information effectively. Addressing it needs this comprehensive strategy, often involving collaboration with ethicists and social scientists to understand the nuanced contexts. Fairness isn't a one-time fix. It's an ongoing process.
Which leads us directly into the broader ethical implications. Bias is one part, but what else keeps researchers and ethicists up at night?
There are quite a few significant ones that demand proactive governance. Privacy and data consent is huge. These models thrive on vast amounts of data, often personal data images of faces, voice recordings, text conversations, biometric information. This raises major privacy and security concerns.
Where does all that training data come from? Is it collected ethically?
That's the question. We need strict regulations, robust security measures to protect this data, and clear ethical frameworks for obtaining truly informed consent, especially when data from multiple modalities belonging to one person is being combined. Techniques like federated learning, where the model trains on decentralized data without the raw data leaving the user's device, are promising but not a complete solution.
Okay, privacy. What else?
The potential for misinformation and deepfakes. Because these models are so good at generating realistic content across modalities, text, images, audio, video, they significantly increase the risk of creating and disseminating convincing false information at scale.
Deepfakes, those fake videos or audio clips.
Exactly. Multimodal AI makes creating highly convincing deepfakes much easier. It becomes harder and harder for people to distinguish real media from synthetic fabrications. Malicious actors could automate customized disinformation campaigns targeting individuals or groups.
That's scary.
It is. Then there are hallucinations. We see this in text-based LLMs too, but the risk might be heightened in multimodal models due to the complex interactions. The AI generating outputs that are nonsensical, factually incorrect, or detached from the provided input context.
Just making stuff up, but maybe based on misinterpreted visual and text cues.
Potentially, yeah. Another concern is labor exploitation. Training these massive models often relies on large teams of human annotators and reviewers, often working in low-wage, high-pressure conditions. They might be exposed to disturbing or traumatizing content during the data filtering and review process. We need ethical sourcing of this human labor.
Right, the hidden human cost.
There's also the risk of over-reliance on AI. If we start using these tools without understanding their principles or limitations, it could potentially hinder human learning, erode critical thinking skills.
De-skilling, in a way.
Could be. And we can't ignore the environmental costs. Training these enormous models is incredibly computationally intensive, consuming vast amounts of energy and resources. Sustainability is a growing concern.
And overarching all this.
A lack of governance. There's currently a significant gap in comprehensive policy frameworks to guide the development and deployment of this powerful technology and mitigate the risks effectively. This uncertainty can threaten public trust.
It really sounds like the power of multimodal AI is a classic double-edged sword.
It absolutely is. The very capabilities that make it so powerful also create or amplify these risks. The ability to combine audio and visual generation enables realistic deepfakes. The need for vast, diverse data raises privacy and labor concerns. Advancing the technology without equally advancing the ethical guidelines and governance structures is inherently risky. Responsible AI development can't be an afterthought. It has to be integrated from the start.
Requiring collaboration beyond just the tech people.
Definitely. Researchers, domain experts like clinicians, if it's healthcare, policymakers, ethicists, the public, everyone needs to be involved in shaping how this technology is developed and deployed responsibly. It needs robust policy, continuous evaluation, and a commitment to transparency.
You mentioned one more specific technical challenge earlier, catastrophic forgetting. Can we circle back to that quickly? It seemed important for practical use.
Yes, it's a critical challenge, especially for developing those multimodal LLM-based agents we talked about.
Remind me what it is again?
It's when you take a large pre-trained model that's good at many things, especially text tasks, and you fine-tune it for a specific multimodal task, say, answering questions about images. The problem is, during that fine-tuning, the model can sometimes experience a significant degradation or even complete loss of its prior knowledge, particularly its ability to follow text-only instructions.
So teaching it to understand images makes it forget how to follow text commands.
It can, yeah. Its performance on the original text-only tasks can decline sharply. Research suggests it might be due to shifts in the model's internal attention patterns, how it weighs text input before seeing an image versus after.
Why is this such a big deal?
It hinders practical deployment. If you want an AI assistant that can chat with you, then look at a chart, you show it, then go back to chatting. You need it to retain both its text and multimodal capabilities seamlessly. Having it forget text instructions after processing an image is obviously problematic.
You'd need separate models or it would just fail in longer interactions.
Right. Simply increasing the training data with more text can be computationally expensive and require lots of data collection. Switching between specialized models uses more memory and isn't efficient for fluid conversations.
So how are researchers tackling this forgetting?
There are several conceptual approaches being explored. One is data replay. Basically, during the multimodal fine-tuning, you continuously mix in extensive batches of the original text-only data or interleave text and image data to constantly remind the model of its previous skills.
Keep practicing the old stuff while learning the new.
Sort of. Another is architectural innovations, designing new model architectures specifically aimed at excelling at both unimodal and multimodal tasks simultaneously. Maybe having specialized side networks or wings that handle visual features without disrupting the core text processing parts as much. There's also parameter-efficient fine-tuning (PEFT) techniques like LoRa, low-rank adaptation. These methods adapt large pre-trained models for new tasks by modifying only a small subset of their parameters rather than retraining everything. This inherently reduces the risk of catastrophic forgetting.
Tuning it more gently.
In a way, yes. And finally, integrating concepts from continual learning. This field of AI research specifically focuses on developing systems that can learn sequentially from dynamic data streams and new tasks without forgetting previously learned knowledge. Applying these principles to multimodal models is key.
It really highlights the tension between building general-purpose AI and specializing it for specific tasks.
It does. The research aims to create systems that are both robust and adaptable. Systems that can learn continuously from diverse inputs without sacrificing past capabilities. That's a crucial step towards truly intelligent, versatile agents.
Okay, so despite the challenges, the field is obviously pushing forward rapidly. Looking ahead now, what's on the immediate horizon? What's the frontier for, say, 2024, 2025?
Things are moving incredibly fast. I think the most dominant trend we're seeing is the rise of unified multimodal foundation models, MFMs.
Unified models, meaning?
Meaning single, powerful AI architectures designed from the outset to process and generate across text, images, audio, video, code, etc., all within one integrated system.
One model to rule them all, basically?
Kind of, yeah. Instead of needing complex pipelines of separate specialized models, you have these one-stop solutions. They're highly generalizable, capable of performing multiple functions with potentially minimal task-specific fine-tuning.
Is this actually happening now?
Oh, yeah. Market analysts like Gartner are predicting a massive jump. They estimate something like 40% of generative AI offerings will be multimodal by 2027, up from just 1% in 2023. It's a huge shift.
What are the implications of this unification?
Streamlined deployment is a big one. Managing one large model is often simpler than a complex web of interconnected specialist models, potentially enhanced performance because the unified model can leverage context and correlations across all modalities more effectively, and likely improvements in overall efficiency and scalability in the long run.
It really signals the advent of more generalist AI, doesn't it?
I think so. A move away from narrow, specialized AI tools towards more versatile, adaptable intelligence. The groundwork laid by transformers and joint embeddings enabled this. This unified nature means less like assembling a toolkit, more like interacting with a single, powerful cognitive engine. Future applications will increasingly be built on top of these pre-trained MFMs.
And these powerful unified models are enabling more capable multimodal AI agents.
Exactly. We should expect a sharp increase in these agents very soon. Autonomous systems that can understand context and respond via voice, images, text, and, crucially, take actions based on this integrated understanding.
Where are we seeing these agents emerge?
They're already starting to transform areas like healthcare, patient monitoring agents, finance, advisory agents analyzing charts and reports, e-commerce, personalized shopping assistants. They can provide highly personalized, contextually aware responses because they perceive more of the situation. And importantly, they aren't limited to just one input type when deciding what to do next. This makes them ideal for next-generation virtual assistants, chatbots, smart devices, offering much more human-like and intuitive experiences.
It's an evolution from AI as a passive tool to AI as an active, context-aware collaborator.
Precisely. Not just responding to explicit commands, but actively engaging, understanding complex, multi-source context, and proactively performing tasks. Perceiving and interacting holistically leads to more sophisticated, truly intelligent assistants.
And on the creative side, generative AI is moving beyond text.
Dramatically so. The capabilities are rapidly expanding beyond just text and image generation. We're seeing major advancements in generating high-fidelity synthetic audio, realistic video, and even complex 3D models, all integrated within these multimodal frameworks.
We've seen some examples like Sora generating video.
Yes, models like OpenAI's Sora, Google's Imagen, and VO2. Runway's offerings, they're generating incredibly realistic and often controllable images and videos directly from text prompts.
The implications seem huge.
Absolutely. For entertainment, gaming, architecture, education. Imagine generating immersive virtual environments, realistic digital avatars, or ultra-realistic synthetic voices and video for dubbing or virtual presenters, all from simple prompts. It drastically speeds up content creation pipelines and democratizes complex media production. Generating 3D models from text or images alone is also advancing rapidly.
It really represents a creative revolution.
It does. Much of this is attributable to advances in diffusion models integrated with deep multimodal understanding. Simple text prompts become powerful creation tools.
So that double-edged sword again, deepfakes, copyright issues.
Exactly. These powerful generative capabilities also introduce significant ethical challenges that need careful management.
Are there specific models from this 2024-2025 timeframe that really stand out as embodying these trends?
The pace is incredible, and it's a fiercely competitive landscape. Everyone's pushing towards more human-like understanding, real-time processing, broader modality support. We already mentioned OpenAI's GPT-4o, which made waves with its real-time, highly integrated performance, especially with voice interaction. Google's Gemini family was significant for its native multimodal pre-training across very diverse data types and its large context windows. Meta's ImageBind showed that unified embedding across many senses 6, in their case, was possible. And research models like NextGPT explicitly explored that any-to-any input-output generation capability.
So many players pushing different aspects.
Right. And this intense competition is generally good news for users. It tends to drive down costs and increase accessibility over time.
You also mentioned advancements in memory being crucial for these agents. What's happening there?
Memory is fundamental if you want agents capable of coherent long-term interactions. If an agent can't remember what you discussed or showed it 5 minutes ago or yesterday, it's not very useful.
Right, it needs persistence.
Exactly. So research is heavily focused on efficient ways to store relevant information, retrieve it when needed, and ground the AI's generation in that memory. There are different types of memory being explored, some stored implicitly in the model's weights, others more explicit. For multimodal agents, the focus is increasingly on contextual, unstructured memory. Think of it as an explicit modality general memory system where the agent can store key information derived from text, images, audio, video, whatever inputs it receives, and retrieve it later.
So it can remember the picture and the conversation about the picture.
Precisely. This is crucial for agents to ground their reasoning in rich perceptual signals and integrate context gathered across different modalities over extended periods. It addresses the limited context window problem, the tendency for models to forget earlier parts of long interactions.
This seems key to making them feel truly intelligent and persistent.
It is. It allows for more sophisticated reasoning, truly personalized interactions based on past experiences, and continuous learning from ongoing multimodal input. It's a major step towards AI that can remember and learn more, like humans do.
So putting it all together, the unified models, the agents, the advanced generation, the memory, what's the overall path forward? What guides development now?
The trajectory seems increasingly holistic. It's moving beyond just raw technical performance to emphasize responsibility, sustainability, and accessibility.
So responsible AI principles are becoming central.
Hopefully, yes. Establishing design principles that prioritize responsibility and sustainability from the outset. That includes research into reducing the massive data and computational demands of these models, which has environmental and economic benefit. Developing best practices for ensuring controllability and alignment with human values, and creating robust frameworks for governing these increasingly agentic multimodal systems, ensuring human oversight remains effective.
What about making them more reliable?
Robustness is key. Enhancing resistance to adversarial attacks. Identifying and mitigating backdoor vulnerabilities planted during training. Understanding the root causes of reliability issues, whether they stem from the data, the architecture, or the pre-training process itself.
And making them usable everywhere.
That comes down to efficiency and accessibility. Developing more lightweight, computationally efficient models. Addressing complexity through techniques like sparse attention, better transformer variants, or specialized hardware acceleration. Integrating these models effectively onto edge devices reduces latency, improves privacy, and supports offline use cases, making AI genuinely more accessible to more people in more situations.
And collaboration is still vital.
Absolutely. Interdisciplinary collaboration is essential for ethical and responsible deployment, particularly in sensitive domains like healthcare. AI researchers need to work closely with clinicians, ethicists, policymakers, patient advocates.
And finally, circling back to that learning challenge.
Continual learning. Solving catastrophic forgetting and enabling models to gracefully adapt to new data, new tasks, and evolving environments without losing critical past knowledge remains a fundamental research direction.
It sounds like the future isn't just about building more powerful models, but building better models, trustworthy, sustainable, equitable, and accessible ones.
Exactly. It represents a maturation of the AI field, where the ethical and societal impacts are becoming central considerations, not just afterthoughts. It requires ongoing collaboration, development of better evaluation frameworks that go beyond simple accuracy metrics, and proactive policy engagement to ensure this incredibly powerful technology is integrated into society in a way that is both innovative and ethically sound.
Wow, what a journey we've taken today. We started by defining multimodal AI, this idea of AI understanding the world through multiple senses like we do. We dove into the mechanics, how it processes diverse data, creates those shared representations or meaning maps, and then fuses that information together using sophisticated techniques like attention. We explored its revolutionary impact and capabilities, the enhanced understanding, the advanced reasoning, that incredible any-to-any generation, and the potential for amplifying human agency, that super agency concept. But we also didn't shy away from the hurdles, the sheer technical complexity of integration and scaling, the persistent black box problem, the critical issues of bias and fairness, especially modality bias, and the whole ethical minefield: privacy, deepfakes, labor issues, hallucinations, environmental costs, governance gaps, plus that specific technical challenge of catastrophic forgetting.
It's a complex landscape.
Definitely. And then we look ahead to the exciting frontier. These unified foundation models, the rise of truly intelligent multimodal agents, generative AI creating not just text and images, but entire audiovisual worlds, and the crucial advancements in AI memory.
And hopefully throughout this deep dive, we've helped you, our listener, get a quick but thorough handle on not just the technology itself, but fundamentally why it matters, how it's already shaping your interactions with technology, and how it's poised to reshape work, creativity, and maybe even how we understand intelligence itself.
Right. It's about gaining that knowledge efficiently but deeply. And as a final thought to leave you with, really consider that idea of super agency. How multimodal AI isn't just about automating tasks we already do. It seems to be about fundamentally reshaping human work, creativity, problem-solving, and collaboration in ways we're probably only just beginning to grasp. The question then becomes, how will you choose to engage with and leverage this evolving power responsibly? Thanks for joining us for this deep dive into multimodal AI. We'll catch you on the next one.